Neuralink is a neurotechnology company co-founded by Elon Musk that is in the process of creating a device with the potential to treat paralysis. A normally functioning nervous system consists of sensory receptors, the brain, and effector organs like muscles. Regardless of how they are linked, they must form a pathway in order for the nervous system to function properly, receiving and propagating electrical signals. If the integrity of the pathway is lost, neurological issues arise. The pathway is usually broken through damage, which cannot be repaired or renewed in most cases due to the complex characteristics of neurons and their environments. In the case of paralysis, the pathway between the brain and the muscle is damaged beyond repair. The goal of any neural interface like Neuralink is to connect the brain to a device that can be commanded to perform a task. There are four components to the successful integration of a neural interface such as Neuralink. The first component is called a reader. The reader is a device that measures activity in the brain by recording electrical activity in specific regions. In the case of Neuralink, this is done by surgical implantation of the device onto the surface of the brain's motor cortex, replacing a coin-sized piece of skull underneath the skin. The device contains up to 3,072 tiny electrodes that act as electrical activity sensors, placed so that the areas responsible for initiating the desired movement can be recorded. This is an engineering achievement that allows Neuralink to record activity more precisely than an external device and at a greater scale than other implantations. Being that Neuralink has only been around since 2016, they are still in the process of perfecting their reading device, so the remainder of the neural interface system is still in the planning stage. However, with the aid of simpler systems that have seen some clinical success, we can get an idea of how effective Neuralink can be in its treatment. Naturally, the next step would be turning these recordings into meaningful movement. First, we must couple these recordings with the movement they initiate in a paralyzed individual. This has been done by Hochberg and colleagues with an array of only 96 electrodes in the motor cortex of human subjects asked to view an action on a computer while imagining themselves performing the action. The 3,000 plus electrodes on the Neuralink reader would allow for a greater scale of movement with much finer adjustments. The coupling of electrical stimulation that is recorded with the desired action is then assessed by the second component, the decoder. The decoder turns these coupled events into a set of commands for a second device to utilize. The decoder makes it so that when the paralyzed individual wants to make a movement, the second device will be programmed to recognize the signal and make the movement accordingly. This connection between the two devices is usually made via Bluetooth. Our third component and second device required for this neural interface is what is known as an effector. This device can be located inside or outside the body, but ultimately receives the commands from the recording device and is able to understand them and make the desired movement thanks to the decoder. If it is inside the body like Neuralink plans in the future, it is likely the setup for the second implantation will be similar to the first, with thousands of electrode fibers being inserted into the brain or spinal cord, depending on the site of damage, with the ability to excite neurons for muscle contraction, resulting in the desired movement. If outside the body, the reader will send its commands to a robotic device that will either be attached to the individual to aid in movement, or will perform the action for the individual without the need for attachment. The latter has shown success in a primate's ability to type. With 96 electrode readers set up, Santhanam and colleagues were able to produce a system in which a primate was able to type 15 words a minute on a keyboard connected to their motor cortex implantation. The final component involves the feedback necessary to enhance the accuracy of the neural interface as a whole. Though the movement you or your robot made as a result of the system may not be exactly what you had desired, with practice and experience, the individual can fine-tune these movements with the new parameters this neural interface has created for them, eventually resulting in improved function. In the case of Neuralink, this will be an especially important step. Given how many movements and degrees within the movements will likely be possible, it isn't hard to imagine the time it will take to master the full range of motion possible.